Thank you. I regret that I cannot deliver my talk in German. I dearly would love to do so, but I'm not capable of it. But I must start by saying how awed I am by the previous lecture from Professor Punch. Just think how Otto Stern would be excited to see my first, my title, Legacy of his work, provides so much beauty and peculiar charm. That's his phrase. It came from his foreword to a book by the first book of molecular rays, as they were called back then, by Ronald Fraser, who had been a postdoc working here in Hamburg with Stern. And in this foreword, which is just 2 pages, he actually summarizes, as he did in his first paper of the famous series of 30 that came from his lab on investigations by molecular beam methods. In that first paper, he outlined in a prescient way the kind of fundamental problems that the molecular beam method is particularly well suited for. And he did that here very tersely in a very elegant way as well. And then you see, he said, I hope that I have been successful in indicating something of that beauty and peculiar charm which so firmly captivate physicists working in this field. He, of course, was a physical chemist, as I am more or less, but I think he was very kind physicist. The things he did, as you've seen already, had opened up so many possibilities, and they're still bearing fruit. Since I had the opportunity to meet Otto Stern when I was a young professor at Berkeley, just starting my molecular beam work, and had been inspired by learning of his work some years before, I felt I should, on this occasion, as I have on others, pass on from the stories as I remember them. I'm very happy that this occasion has given me a chance to learn from Alan Templeton in particular, and others too, still more stories about Otto Stern. But there will be a wonderful contrast between the brilliant talk you heard, absolutely awesome talk just before mine. I would say we might have to modify this statement, beauty and passionate charm in the case, although that word would apply, I think, just as well for what Otto Stern and followers of him have felt about their much less awesome experiments. The particular experiment of Otto Stern that I'm going to emphasize in my talks later in the talk involves just 2 significant digits. I counted 15 in your 1s to 2s measurement, and I think 14 in the Rydberg constant. So a different realm altogether, but equally offering beauty and inspiration, or so I hope we will see. Now, I wanted to give next a photo you haven't seen among the many, but notice he's smiling just as he is with so many of the other photos. This one was taken by I.I. Rabi, and for I don't know quite how many decades it was in his office, and it has an essential smile of Otto Stern shining on all of us today, especially on this sunny day here in Hamburg. But I put it here because in 1988, the centennial of his birth, which was celebrated here in a convocation, I had just a year or so before that had the impression that it might be overlooked entirely. So I wrote to various friends in Germany, including Herschel, who was then the editor of Zeitschrift for Physique, where the series of 30 papers, CERN's lab, were published. And of course, then I got appointed the guest editor. So we collected 30 papers in the special issue of Zeitschrift for Physique, including a poignant preface from I. Stern, Robbie, who was actually on his deathbed at the time. But his remarks to John Rigdon, who put in the paper, and this was the first figure in the paper, as well as other things. I mention it because some of you may want to look there, as well as some articles I'll mention by others who have worked with Stern directly. I will tell some stories. You already saw from Professor Kettley yesterday a tree of people, and you saw a tree of scientific discoveries and methods just a little while ago, and there is such for Stern as well in various places that you may want to look at in more detail. This article by attorneys Horst Schmidt-Markham right here, you should stand up, and Branislav Friedrich just appeared, I think, just last year in Nobelpreis Physique, and I would recommend this very, very strongly to all of you who by now, if you aren't already great fans of Otto Stern, will want to learn more. Some of the stories I'm going to mention are there, but maybe not quite all of them. Then the next one is a happy occasion. About a year ago in Berkeley, I had an opportunity with Alan Templeton to pay a pilgrimage, I would say, to visit the desk that Otto Stern had made for him decades before. It was a gift, I understand, from his sister, who commissioned a skilled woodworker to make this beautiful desk, and it was blessed by Alan's parents. His mother was a sister or aunt, I guess, of Otto Stern, if I have it right, and they wound up donating it to Berkeley, where he was, as you know, in his retirement years, very happily interacting with people. And it was there that in 1960 I got to hear stories from him personally. The way that came about was we just had, the year before, started building an apparatus and had some results. And although I was in the chemistry department, it was a physics department that invited me to give my first seminar on those results. Naturally, I started out talking about Otto Stern. I noticed a couple professors right over there to each other, turning and swiveling and looking at the audience. And afterwards, one asked me, "Did you know Otto Stern was in the audience?" Well, my first knowledge of Stern was of the work he did back in 1920 and 22, the velocity analysis experiment, the Stern-Gerlach experiment. I had no idea he was still on the globe, much less. But I had noticed all by himself up there, it was a little sparse in that region, the left field of the audience. The little fellow, all dressed neatly in black with a tie and all. I've learned now from Alan that Alan doesn't remember seeing his uncle without a suit and tie, and he even wondered if he slept in it all the time. And he looked to me a lot like Charlie Chaplin. And then within a week, Howard Sugar, the young faculty member in physics, arranged a little meeting, and we had supplied tea and coffee and cookies. And at first, Otto Stern seemed shy, very shy, but the more tea he drank, the more he told with great zest and laughter and all some of the stories that I want to mention now. And the first of those, I think I have here, has to do with the velocity analysis experiment. When that was the first thing I heard of as a Stanford student in a course taught by Walter Meyerhoff. I'll want to mention a little more about him later. It was a digression from the main theme. The topic of the whole course was statistical thermodynamics and kinetic theory. But I think in not less than 3 or 4 minutes, he said a few words about this experiment. He did not show a picture. There weren't any PowerPoints back then. But it was such an exciting idea that you could have these streams of molecules flying through a vacuum, far enough apart, dilute enough so they didn't disturb each other. And then you said, well, gee, that's the way for me. I was thinking we should cross another such stream, and there'll be some collisions, no chance of anything other than pairwise collisions, one from each stream under those conditions. And then the detectors of products that were just freshly born, if you could detect them well enough, you would get information carried by these newly born molecules about the forces involved in forming them from the reactants. Well, of course, that's the holy grail for chemistry. When I talked to my advisor, he laughed and said, yes, people naturally are doing such a thing, but it's completely impractical, not enough intensity. And indeed, when a few years later, we were actually starting those experiments at Berkeley, some well-known people referred to it in public as the lunatic fringe of physical chemistry. What I hadn't anticipated was that by being a rash young faculty member who was pursuing a lunatic fringe project, I attracted graduate students who wanted to work on the lunatic fringe. They weren't satisfied doing more civilized kinds of things. And that's why it all worked, really. That's one reason. Another reason is Otto Stern, when you looked at his work, and his colleagues had really prepared the way for us to do this kind of early experiment. But look at this one. It looks a little different than the pictures you often see in books of rotating disks. So there's lots of slots, so they select the velocities they can get through these spinning disks. Otto Stern back then, what kind of detector did he have? He didn't have any way of detecting the things as we can now. We can use lasers even, as well as super sensitive mass spectroscopy, all kinds of neat things. What he had to do was rely on collecting the actual atoms. How do you tell their velocity if you're going to collect them on a surface? Right? You're going to lose that information. Well, he made this merry-go-round. He has a heated silver filament here and has some connections that maintain the current heated as he rotated this contraption like this. And the stream of atoms went through some slits, and they would be collected here. And because it was rotating, of course, his detector was moving out of the way of these atoms. They actually were traveling about 660 meters per second on average, and you could almost have a graduate student cranking this thing, because he had a little more sophisticated rotation. But it's rotating only 15 meters per second, peripheral velocity. But you see, he could rotate one way and get a displacement of the beam from what it would have if it were just sitting still, and then rotate the other way. And then he measured the difference between the two to amplify the accuracy. And he was able to test, which was his objective, the prediction from Maxwell-Boltzmann theory of the distribution of molecules in the thermal environment. Well, that was the first story that we heard at this meeting with him. And he mentioned how he mailed out what we would call preprints, and he got a letter back from one colleague who pointed out that the discrepancy he had found, which was not very large, but noticeable, concerned him with the Maxwell-Boltzmann prediction. Actually, might be because Stern had left out a factor that should be there. The fact that he had these slits meant that he was really measuring flux rather than number density. So instead of the usual form of Maxwell-Boltzmann, that would v squared for velocity times an exponential term, you need a v cubed, an extra factor of v. Because if all of you were to wisely race out already, to empty this room, the faster ones would get there first. And you have to allow for that flux. So when you put that factor in, it agreed much better. And then I can see him now, he laughed heartily, saying, that letter came from Albert Einstein. Of course, I only learned later that Stern actually had been, as you've heard already, a postdoc, the first postdoc who worked with Albert Einstein. So that was the first story I wanted to mention. I don't think I think I may have mentioned that in my Nobel lecture in '86, and it was the thing that got me concerned to make sure that his centennial of his birth in '88 was celebrated, but I didn't know you were going to celebrate it here, because I hadn't heard about it at the time when I begged Zeiger for Physique to have a special issue that I mentioned already. The second story he told about was his gratitude to Max Born. I think you may have mentioned it in your welcome remarks. The early days of the 20s, you all know historically, there was this rampant inflation, awesome inflation. If you're a stamp collector, you know all about it. 20,000 marks to mail a letter, and so on. And that, of course, had an enormous impact on doing any kind of work. But there's tremendous interest in Einstein's theory of relativity. And Max Born gave public lectures, collected the money from that, and supported the Stern-Gerlach experiment that you heard about. He also expressed his gratitude to Hamburg, who was so generous, and you heard a little about that already, bringing him here. Brand new university, I think you said it was founded in just 1919. It called to Otto Stern in 1923. Took a little while to build some buildings and all, and took therefore 2 or 3 years before his molecular beam enterprise began really cranking. But he spoke very happily about those considerations, joking about all the troubles he caused various politicians to see the Institute happen. He also said that since his PhD was in physical chemistry, but he became a privat docent first in Zurich when Einstein moved there from Prague, where he had been at the time Stern first joined him. And then later at Frankfurt, where was the next stop for Stern, he would be teaching physics courses. So he had to study late at night to prepare his lectures. And so he got in the habit of drinking very strong black coffee, and now, ever since, he could not go to sleep unless he had some black coffee first. So that was one of the stories I thought some of you might find of some interest in the human psyche. Then, when he was asked about how he conceived the Stern-Gerlach experiment, he said something that I'd like to point out to graduate students and postdocs. One morning after a seminar, which had raised the question why gases were not observed to be magnetically birefringent, on the Bohr model, which is what you had back then. You didn't have in 1920 yet quantum mechanics. Of course, you have these planetary orbits. So you would imagine if you had a magnetic field that could interact with the magnetic moment generated by the charge of the electron whirling in its planetary orbit, you could orient that in space, and then if you put in polarized light one way or another, you should see a different effective index of refraction by refringent. But no one had observed that. And he woke up thinking about the seminar, and it was too early to go to the lab because in Germany he explained everything is so well organized you can't go before a certain hour. I don't know if that's still true. And it was too cold to get out of bed, just the way it was a couple mornings here ago. I thought of that. So he stayed in bed and thought about the seminar. So that's a very good thing for students, postdocs. I don't know whether someone thought of the frequency cone bed, but I know Towns thought about the basic idea of a laser some 30 or 40 years after Stern woke up in his bed while eating a sandwich on a bench in Washington, D.C. You aficionados know that. So there are opportunities like that to come up with very fundamental ideas. So he also emphasized in another story that he recruited Gerlach as a collaborator because Gerlach was a skilled experimentalist, no doubt about it. And Stern said Stern was not good with his hands. In fact, he noted that each part of the apparatus that he constructed had to be remade by Gerlach. Good thing for young professors to realize this too. If you can attract some students eager to do lunatic fringe work, then let them do it, boy. Let them do it. So Stern also said that, as in his memory, they're hardly ever able to get their apparatus to work before midnight. That's still true. It was in many times in my experience. Finally, I have to mention Stern's cigar story, which I have told very often. It launched a research project when I was invited by Horst to take part in 2002 in the dedication of a new experimental physics laboratory at Frankfurt, named in honor of Stern and Gerlach for their famous experiment done there. Of course, that launches to the cigar story. This is one of the photographs you've seen already here. But in my telling of what I thought I remembered, it goes like this. I wrote it in first person form, as if Stern was saying this. Of course, I didn't remember his exact words, but I was trying to recreate the spirit of what I thought he said. After venting to release the vacuum, Gerlach removed the detector flange. Again, it was detecting silver atoms in an experiment, going through the magnet and all, to see if they could detect the orientation in space with the spins. You now know what spins. They didn't know what spins. Nobody knew about spins back then. They thought it was the angular momentum of the electron. But he could see, no trace of the silver atom beam, and handed the flange to me. With Gerlach looking over my shoulder as I peered closely at the plate, we were surprised to see gradually emerge the trace of the beam. This is what I remember, or thought I remember, of him describing. Finally, we realized what had happened. I was then the equivalent of an assistant professor. My salary was too low to afford good cigars, so I smoked bad ones. These had a lot of sulfur in them, so my breath on the plate turned the silver into silver sulfide, which is jet black, so easily visible. It was like developing a photographic film. So I would always, I've told this so many freshman chemistry classes to graduate quantum mechanics, and I would always say the punchline. So you see, bad breath had a key role in an epic experiment. However, the truth is sometimes not quite as exciting as it gets modified over time. When Bretislav worked on this, we found that it couldn't have been quite that way. I thought this was actually referring to the Stern-Gerlach experiment itself, and it was really the splitting of the beam that appeared. That wasn't true, because Stern wasn't physically present then. He had been called to a position in Rokov instead, and it was they were by that time using a photographic method of dividing rather than just cigar smoke. But we thought, because of the meeting that Horst invited to, we should check up on this at last. So here's Bretislav setting up an apparatus at Cambridge, our lab, and alignment is absolutely crucial for these kind of experiments of all sorts. And here's aligning the cigar very carefully. I like that smile on his face. I think Otto Stern has a similar one right now. And here he is. And then here we are emulating this legendary detection of the traces. But it turns out that, boy, you just give a puff of cigar smoke and wham, the traces leap right out. But we actually got a variety of cigars to test. Good ones, cheap ones, and so it didn't make any difference. With just bad breath from smoking the cigars, developed well enough at a level of what we thought was corresponding to the level that they had in their experiment. It took them about 8 hours to collect enough silver atoms to detect them. So that's the range of stories I wanted to tell you, but I want to say a little more about Walter Meinhof, from whom, as I mentioned already, I first learned about Otto Stern and molecular beings at all, because it was only when I went to Frankfurt and learned more, and I mistakenly thought for a while he was connected directly with Frankfurt, but he wasn't. But Walter was born in 1922 in January, and the paper with the splitting of the Stern-Gerlach came out in February 1922, as you know. So there was that connection directly, in a way, with Otto Stern's work. The Stern-Gerlach experiment, I hadn't heard about that. It was only the velocity experiment we heard about from Walter Meinhof. But I learned that his parents were Jewish. In fact, his father, Otto Meinhof, received the Nobel Prize in that same year, 1922, for his work on oxygen metabolism connected with lactic acid. So when your muscle gets sore from too much sitting and running, why think of Otto? But it didn't help. That is, when the Nazis came in, Walter and his siblings, his mother had insisted they be raised as Lutherans, and they were nominally, but that didn't help. They were being bullied so much they had to flee first to France, and then an American named Varian Fry was responsible for essentially rescuing him at a later stage, and eventually he got to United States, and Walter got his PhD at the University of Pennsylvania. He was called by Felix Bloch and Leonard Schiff to become a professor in 1949 at Stanford. And the course I spoke about, where he is a digression, said these words about Otto Stern that changed my life, and therefore indirectly that of quite a few other people, I heard just a few years later. So what I had no inkling of then, but appreciate so much now, is that the fact he was driven out by so many Jewish people, or people of Jewish ancestry, meant that that's why I heard about Otto Stern. from Walter Meinhof. I mean, might not have happened, or not happened in the right time when I was a brash young guy and just thrilled to the idea that, oh, this is the way to do chemistry. So, you know, history works kind of curious ways. All kinds of contingencies happen. And we don't know why, but we go with the flow, especially if it's a molecular beam flow, in my case. So that's what I wanted to mention. Now, the part of Otto Stern's work I wanted to feature here today, I've talked about others and various other papers, but is his work that really launched nuclear physics, as you've already heard, the measurement of the magnetic moment of the proton and then the deuteron as well, which indirectly allowed them to determine the magnetic moment of the neutron as well. This is I especially wanted to do because it turned out Walter Meinhof was involved at Stanford in early developments of nuclear physics at Stanford. He was very much involved with the Stanford Linear Accelerator, SLAC and all. And he wrote a book on elements of nuclear physics and all. And he collaborated in that direction with Wolfgang Panofsky, who was another one of my teachers at Stanford, also an immigrant in 1933 for the same reason. So it makes you think, do we have all these connections? But this picture is especially interesting to me. It's a picture of the apparatus that is included in Ramsey's book, for example, and many other places, as the apparatus used by Esterman, Frisch, and Stern in Hamburg. And I'm sure it's right. However, in 1937, when Stern had to move, as you know already, to the United States, and in the Carnegie Institute of Technology in Pittsburgh, they built an apparatus. They published a paper because they repeated the experiments on the proton and deuteron. And this is a picture they have in that apparatus. It's identical to the one in Zeitschrift für Physik that was published in 1933. In 1933, they had only to end of August to clear out. Actually, most of the German universities, the Jews were chased out earlier, but apparently Hamburg was far enough away from Berlin, and the attitude of people here was, we have a contract we must honor with these people. We have to keep paying them till the end of August, so we will keep them teaching. But they were allowed still to go into the lab, which many other places are immediately not, from April or whenever that law came down, not even allowed to set foot anymore. But the result was they worked like demons, and in that year of 1933, 12 of the 30 papers came out. Obviously had partly been prepared for years before. But this apparatus, as they said in the paper from Carnegie in 1937, it was essentially the same. Well, it is the same picture. So I don't know whether, they just said, well, we'll just print the same picture or what. There's also a description in Esterman that he had rebuilt part of the apparatus at Frisch, and it turns out that all these have the same picture. So I just mean that it was a lot harder than it is now with PowerPoint and so forth to generate such pictures. At any rate, the point is, it's a relatively complicated apparatus for that time. And there are charming stories about it. Otto Frisch, who very distinguished physicist, and did much work as a postdoc, epic work with Stern, he liked to tell the story of a visitor who came and was remarking about the complication of the apparatus, and Stern said in reply, "Yes, it's too bad that our ancestors lost their prehensile tails. It would be convenient sometimes to have that extra grip." The visitor then very astutely responded and said, "Yes, Stern, however, then you just make your apparatus all the more complicated." Probably true. At any rate, you need to appreciate, and the reason I selected this is partly the connection with Walter Meyerhoff, but also I think in talking about these primitive two-digit accuracy experiments, the inspiration you would hope that young people get from it is to have some appreciation of what the historical context really was. Now, it's not possible for us to do that. We can't really go back and realize how many things are completely mysterious and mixed up and misunderstood and so forth in that way. But it's good to try to the extent we can to get some idea, because the same is still true. There are a few rather major questions. What is dark matter, dimension? What is dark energy? And many others in physics today. And they're somewhat similar to mysteries back in the 20s and 30s. So here, just quickly, I run down some dates you should be aware. Bose-Einstein and Fermi-Dirac statistics were understood as, of course, the symmetry property imposed on the wave function. If I find, here's a simple tiny laser. Depending on whether you have bosons or fermions, you need an interchange of identical bosons to be symmetric and antisymmetric, as you know, for fermions. And just a year or so later, Denison recognized what we call the orthopara conversion of hydrogen. It meant you had two nuclear isomers of hydrogen. We call it para when the nuclear spins are opposed, and the adjacent protons in the hydrogen molecule. Ortho when they're parallel. And the rate of conversion between these two species by interaction, especially with magnetic impurities and things like that, and flip the spins, was very slow at ordinary temperatures, so that he recognized that the heat capacity, which was very, very puzzling for a while, is really because you have a mixture ordinarily of 75% ortho and 25% para in ordinary conditions. But with catalysts, you can speed that up and you can separate para from, but that was only recognized and developed in the next few years. Dirac in 28, of course, did his sensational theory of the relativistic hydrogen atom, and that made it clear that the spin was a half for both the electron and the proton, and also predicted correctly the magnetic moment, one Bohr magneton, we call it, for the electron. And so that seemed to imply that for the proton that had the spin on that, its magnetic moment should be the same as the Bohr, as the electron, except instead of the mass of the electron entering in, the mass of the proton should come in, which is about 1836. So a much, much smaller moment, we call the nuclear magneton, for the proton. That was, especially Stern's very good friend, Wolfgang Pauli, eminent theorist, but also essentially all other theorists at the time, told him he was wasting his time to try to do this very difficult experiment of measuring this very small magnetic moment, essentially 2,000 times smaller than the original Stern-Gerlach experiment that worked on the electron moment. Appreciated by then was due to the spin, not the orbital angular momentum of the electron. And Stern said just the same thing he said about his velocity analysis experiment. He said, well, no one really thought that Maxwell-Boltzmann prediction for the mean velocity, which is what he could measure, was wrong, but it was still satisfying, the test of it. Well, that was his response here too. He took a certain pleasure on one event in which he already knew from their first rough primitive experiments, they didn't have their full control of their experiment yet, but he knew it wasn't going to be one nuclear magneton. It wasn't just going to be the mass ratio of the proton-electron and determine the magnetic moment. It had to be a lot bigger. But he got all these theorists to predict, and they all said it had to be one nuclear magneton, which the Bohr with the Dirac theory is what you would expect. And if you've heard already, the result, the obtained was about 2.5, or 10% or so. And that means that you can't be a Dirac particle. It has to be more complicated. That was, of course, a fundamental thing. And even today, you can't calculate the magnetic moment of the proton. It's been calculated by quantum electrodynamics for electrons to, I think, 11, 12 figures. But I don't think the proton may have more than 1, 2 at most. So the experiments now, of course, now about 7 place accuracy, but quantum chromodynamics, as it's called, the theory of strong force, is not up to it yet. So there's still that challenge all the way back to this, what was thought of people to see a lunatic experiment by Stern and his colleagues. So look what, it wasn't until 31 that deuterium was discovered. It wasn't until 32 that the neutron was discovered. And here they are in 1933, under very bad conditions. They didn't know when Nazis might come in any minute and kick them out and so on, working like demons to try to do this thing that Stern in his 1925 paper, the first one of the series where he listed the things he thought they could do, and wound up in the less than 10 years he was able to work here in Hamburg. They actually got a good start on every one of those things, and a few things more. So that's the thing we want to celebrate, and I think I will skip some details here. This is from a lovely paper by Esterman in Atomic American Journal of Physics in '75, and what he shows here is what you would predict, what they anticipated beforehand, the deflection pattern would look if you had no velocity spread, because the deflection of the magnet depends on the speed of the little atomic magnets going through the inhomogeneous field. The key thing is in the Stern-Gerlach experiment. So you don't get sharp lines like this, but this was their prediction. And the thing is that what they undertook to do was determine the magnetic moment of the proton in a very difficult way, because they couldn't run a proton. The charge on that makes it completely impossible to measure any magnet bang into the electrodes. You couldn't do it with a hydrogen atom, as wonderful as it is, because the electric magnetic moment is 2,000 times bigger. Under the high field conditions, they felt it was feasible to get enough deflection to measure the magnetic moment of the very weak, very small magnet of the nucleus. Theory predicted that even without any contribution from the nuclear magnetic moment, just the rotation of the hydrogen molecule will generate a magnetic moment, because you have currents as the electrons move. That was 3 nuclear magnetons. That's 3 times higher than the predicted 1 nuclear from this nuclear spin in the ortho case. There's only in the ortho case do you have net nuclear spin. In the parallel one, they cancel out. So what did they have to do? In order to determine the contribution from the rotational effect that is not connected at all with the nuclear moments, Esterman had to go to Berlin to Nernst lab and do this brand new thing that a few other people do, separate pure para so they could measure the rotational moment of that in their deflection experiment. Well, actually, there's no deflection in cold, very cold para hydrogen because the nuclear statistics say that for the para configuration of the nuclear spins, you have to have rotational states only 0, 2, 4, the even ones, whereas for ortho, you have to have odd ones. But so for para, if you're in the lowest rotational state, then there's no nuclear moment and there's no rotational moment. So he had to make measurements heating up the para to various temperatures to calibrate it, because if you heat it enough, you get a contribution from J equal 2. That's what these lines here mean. These little shifts. Shift for rotation, shift for the nuclear part. There's no shift for the nuclear part, of course, for the para, and there is for ortho. But it turned out that when they actually measured it, the shift was about 0.85 for pure rotation in para. The accurate one now to several figures is 0.88 something. Not too bad. And within they could correct for the ortho case, where you had both. Actually, they didn't have to do experiments with ortho. They could run just mixed hydrogen, 75% ortho, 25 para, because they ran those very cold, 90 degrees K, was as cold as they could get, but it was cold enough, so everything went down to J equals 0 for the para, didn't contribute, and J equal 1 for the ortho, that still had rotation, but they could correct that from what they measured with the para. You see, that's pretty tricky. This shows you in the next slide what their data actually looked like. This is from the 37 where they got their data. This is the magnetic deflection. Not very impressive, right? Except if you look at the scale, those are hundredths of a millimeter. Hundredths of a millimeter. This is the beam. It was about this long, and they were deflecting this thing hundredths of a millimeter. What they actually measured in the end, you can see these little bumps here, and you saw the little stick figures before they came from the wider spread. The splittings you should get from the nuclear moment of 1, which contributes to 0 deflection, and then plus and minus deflection for the 1 unit of angular momentum. You always get that pattern of 3. They actually measured just the decrease here very accurately. You can actually determine some here, but all of this has to be averaged over velocity distribution and so forth. It turns out that the most sensitive part is right in the center. So it's really that decrease that determined their number, 2.5 nuclear magaton. In 37, they added to this. They were able, still at Hamburg, as a result of the gift of a half a liter of heavy water. Notice heavy water with heavy deuterium, you only got in the late 1931, and here they are, mid 33, having to do chemistry. For example, they got heavy water from G.M. Lewis at Berkeley, this half a cc, 85% enriched in deuterium, and Esterman had to turn that into hydrogen, not completely trivial thing to do, and then carry out these experiment, the same kind of experiment with deuterium. And they discovered that the moment of deuterium was a third of that, much smaller than the proton. That was a big surprise because the deuterium, of course, is a proton and a neutron. It was thought that the neutron shouldn't have any magnetic moment at all, and therefore the deuterium atom should have the same magnetic moment as the proton. But it turned out, because it's so much smaller, you could work back and find out that the neutron had to have a magnetic moment minus 1.6 nuclear magneton. It's clearly not Dirac either, it goes spin 1/2, and it's optically oriented. They got all of that from basically this kind of experiment on H2 and D2. But here in Pittsburgh, later, they followed up to get HD. Now they see, again, it's the shift to the center that determines what they're after. But why does it have this pattern? Well, it's easy to see. In the case of HD, you don't have ortho and parallel. You don't have bosons and fermion pairs, identical particles. You've got one of each. So the result is that there's no center line at all, because if you can think of it, first approximation, since the moment of deuterium is only a third of that for the proton, splitting due to that, it's pretty small. You just mainly is the proton splitting, and the proton splitting just gives you a plus this way and a minus that way. No red line, because the proton is spin 1/2, whereas in H2, ortho had total spin of 1, because you had two spin 1/2s adding. So that's a very pretty thing, and of course that's what allowed them to get a somewhat more accurate number for the magnetic field of the neutron and deuteron. So I hope in this to have given you some appreciation for what these low precision but beautiful experiments are. And just, I should quickly, I jotted down a few notions to remind people we've already recognized nuclear magnetic resonance, optical pumping, amazing the laser, atomic clock. All of those really are descendants of sorting quantum states according to phase quantization. And of course that led to many discoveries. We see now lamp shift even for exotic relatives of the hydrogen atom, the electron replaced by a muon and all. Anomalous moment of the electron was also determined from this basic thing. So those two things led to QED. The anomalous magnetic moment of the proton and neutron, which really presaged the development of quantum chromodynamics, which, as I emphasized, still can't clear up the actual numbers for the strong nuclear force. So bringing it down to the cosmos and to grocery stores, we have from all this, it means to probe nuclei, protons, galaxies, image bodies, brains, magnetic resonances, imaging, and perform eye surgery, read music or data from compact discs. I mean, there are even proposals that I understand to put a barcode on the forehead of every newborn, so to simplify a lot of things you go through life. And DNA base pairs, even. So every time you check out in groceries, think of Otto Stern. It goes back to. So just a few more words in this direction. I thought it would be fine to quote people who worked on Otto Stern directly. Here's Emilio Segre, who wrote a wonderful biographical essay about him in the National Academy. You can find all these references, of course, in particular to the wonderful article I mentioned that involves Horst and repeated attorneys and Bretislav. So here's what Segre, who worked with Fermi, of course, before he went first to work with Stern, and later at Berkeley, he got the Nobelpreis as co-discoverer of the anti-proton, which incidentally I heard from Jerry Gabourez just before coming here. They now feel they have the magnetic moment of the antiproton and it's identical to 4 or 5 figures with that for the proton. When Professor Hensch gets done with it, that might not be true anymore for those first 4 or 5 digits. They agree perfectly. So Otto Stern would be chuckling about that. Here's one of the greatest, Stern, one of the greatest physicists of the century. He wrote relatively few papers, but what power were those he did write. He published a total of 60 in his career. The reader does not know whether to admire most the simplicity and profundity of the theoretical ideas, the ingenuity of the techniques employed, or the inescapable force of the conclusions. And then Frisch, Stern was rather clumsy. Moreover, one of his hands invariably held a cigar, except when it was in his mouth, so he was disinclined to handle any breakable equipment. Yet Stern, in a higher sense, is the superb experimenter. Others emphasize this as well. In using a new apparatus, he left nothing to chance. Everything had been worked out beforehand, every detail of the performance carefully checked. Stern would calculate, for instance, how much beam intensity expected to get, even though that was a very lengthy and tedious calculation, which he always did himself. He could not predict the intensity very accurately, but if it fell short by more than 30%, he felt that something must be wrong, and the fault had to be tracked down. I've never seen anybody keeping such strict control of his instruments, and it surely paid off. There's other testimony to that effect. Finally, the point remarks by Robbie that included in the Lectures for Physique special issue I mentioned in 1989. From Stern and from Pauli, I learned what physics should be. For me, it was not a matter of more knowledge. I learned a lot of physics as a graduate student. Rather, it was a development of taste and insight. It was the development of standards to guide research, a feeling for what is good and what is not so good. Stern had this quality of taste in physics, and he had it to the highest degree. As far as I know, Stern never devoted himself to a minor question. And then later on in his remarks, Robbie said this, which I think we should include. I am extremely regretful that Stern's scientific personality did not make its influence on American graduate students. His qualities of physical insight into basic physics were rare. His experiments had style, that quality of beauty that links the scientist to the artist. In this day, the qualities that were so great in Stern are of central importance. If physics is to remain an adventure of the human spirit. That was Robbie, and that's, I think, a fine testimony. I think I have just one more thing to show you. In the Lectures for Physique, I thought it was appropriate to add the foreword to that issue. These verses exchanged by Arnold Sommerfeld and Max Planck. I won't try to read the German right now, but here's Sommerfeld to Planck. You nobly made arable a vast new ground wherein I have here and there a sprig of flowers found. And Planck very graciously replies to Sommerfeld, what you have picked and I have picked, these we will bind together, entwining thus a fair bouquet from gifts we send each other. I think that's a fitting thing for what this symposium does. And finally, I recently had an occasion to speak before, I think there was 15 Nobel laureates in physics and chemistry, and I asked them, and any of them looked at the reverse of the Nobel medal? Raise your hand. None of them raised their hand. I bet you have, and you have, and you have. Right. So this is what the reverse side looks like. You all have seen one with Alfred Nobel, appropriately enough. The reverse side has a figure that, notice they're both feminine figures. And they're kneeling, this figure is kneeling in the billowing clouds, and this one's erect. This one's labeled, you can't see it too well, Scienta. And Scienta has a little scroll, no question, gripping it tight for the precious knowledge we've so far gained. But she's gazing upward intently at the erect figure who has a cornucopia here. And that's Lego Natura. So with an ancient motif listing the veil of nature, this exemplifies so well the kind of science that we celebrate here in honoring Otto and that you've seen on the. So thank you.